All right, let's take a quick look at the warm-up problem. Let me give myself a little more room. The first thing we want to do is find RT. We recognize that this is a series circuit. Current leaves, whatever current goes into R1. Whatever comes out of R1 has to go into R2, out of R2 into R3, out of R3 into R4. So it's a series circuit. So in a series circuit, RT or REQ is, in this case, R1 plus R2 plus R3 plus R4
But
plus
it's
R.
not like 20,590 ohms.
Say that again?
20,590 ohms.
I haven't gotten that far yet. Are you saying that that's the answer?
Yeah.
It might well be. I haven't gotten that far yet. 680 plus 2.7K plus 12K plus 4.3K plus 910. That makes the REQ. So 4.3 plus 2.7 is 7K plus 12K is 19K. 19K, this is 1.59K. So 19 plus 1.59K. 19, 20, 20.59K. Is that what you came up? Is that what you came up with?
Yeah, that's what I got.
And then we were asked to solve for IT. IT is going to be VS over RT. So I've got 20 volts divided by 20.59 K ohms. So IT is going to turn out to be a little less than 1 milliamp. Somebody with a calculator, would you come up with?
.971 milliamps.
0.971 milliamps. Is that what you said?
Yeah.
Okay. So then we can say that V sub R3 is going to be IT times R3. So they have 0.0971 milliamps times 12K. It's going to be 11 and change volts. Anybody do that?
Yeah, it's 11.65. Well, actually, if you round, it'll be 66.
11.66 volts.
Yeah.
And then last but not least, let me give myself a little more room. V sub R4 using voltage division. Voltage division says we're going to put the one we want to find the voltage across in the top, so it's R4. We're going to put the total in the bottom, and I'm just going to save myself some time and say it's REQ. Would be R1 plus R2 plus R3 plus R plus 4 plus R5 times VS. So I've got 4.3K divided by 20.59K times 20 volts. So V sub R4 4.17 volts, 4.18 volts. Any questions on any of that? Okay, so that was a series circuit. And last class when we left off, let me go back to that one for a second. We had started working on parallel circuits. And we had said in a parallel circuit, oh, before I do that, let me bring up multisim because I know you did this in lab, so we might as well just reinforce that. So in multisim, if I wanted to, I could check my answers. And so if I went and got a multimeter and brought that down, I just take that and make it a current.
We cannot see multisim.
Oh, thank you. How come I didn't? I thought I shared that. All right. There we go. So if I bring down a multimeter and I open the multimeter and I set it for current and I set it for DC, now if I just take and drag this and drop it, I can remove that little chunk of wire. And now I've got my ammeter in series. And if I bring down another multimeter, remember current meters always go, current measurement, you're always in series, voltage measurement, you're always across. So if I now take this meter, and we're going to leave it on DC voltage, I'll put that up there so it's next to it. And we're going to connect across, the plus goes on the top, minus goes on the bottom, because as we go through the circuit, plus current goes into the top end of R3, that makes it the positive end, comes out the bottom end of R3, makes that the negative end, so we put the appropriate points in the circuit. I'm going to move that a little bit out of the way. And we'll wire this circuit in. Let me set that up as a voltmeter as well. And now connect that up. And now if I run this, and I can stop my simulation, I've got my voltage. And doing it. So now we see that we calculated 0.971. We measured 966 microamps, which is 0.966. So that's certainly close. We calculated 11.66 we got for the voltage across R3. So we calculated this voltage to be 11.66, which is exactly what we got. We calculated the voltage across R4 to be 4.18, and that's exactly what we got. So indeed, it's an easy way. If I give you homework problems, you can use multisim to very easily check your answers to see whether or not they're in close or not. It's a nice little instrument. All right, any questions on the problem we're using multisim? You did this in lab on Thursday, yes?
Yeah, we did.
Okay, so they should have been This should just be old hat. You did it. Did you do the circuit that we had done in class and use it in lab?
Yeah, we made like a PowerPoint.
Oh, okay.
Not a PowerPoint, an Excel.
Okay. An Excel spreadsheet to do the math. Yeah, that's another thing that you can very easily do and set up an Excel spreadsheet. And you can make it for as many resistors as you want if you just do the sum over a range. If the cells are blank, it doesn't matter. So I could make it the Excel spreadsheet for 10 resistors and use it with 2. But I don't know if you went into that or not. All right. All right. So when we left off, let me go back to where we were before. So when we left off, we were looking at parallel circuits. And we said that our rules for the parallel circuits were that in a parallel circuit, the resistors share the same 2 nodes. So we said that if we went and did a list of where the resistors are connected, we would see that all of the resistors connect to the same 2 nodes. In this case, node A and node B. So R1 connects between A and B, 2 connects between A and B, and so on down the line. VS connects between A and B. So parallel components share the same 2 nodes. That means that since V sub S is connected to A and B and all of the resistors are connected to A and B, all of the resistors have the same voltage. So if the power supply was 12 volts, R1 would have 12 volts, R2 would have 12 volts, R3 would have 12 volts, 4 would have 12, 5 would have 12, and so on. And we said that the current in each resistor would be different unless the resistors are all the same value. Okay? And then we did a comparison between series and parallel. How come that didn't change? I clicked the wrong. No idea. We said that in a series circuit, there was only, if you made the list of what's connected where, you'd only see one letter that matched on 2 resistors. So they only had one common node, whereas we saw in parallel, they all share the same 2 common nodes. We said in a series circuit, the current is the same in each resistor. In a parallel circuit, the current is different in each resistor unless all the resistors are the same. We said the voltage across each resistor is different unless the resistors are equal, but the voltage is the same in a parallel circuit. Okay, so those were where we left off last class. So let's do this. Let me get to today's PowerPoint. Not PowerPoint. Oh, before I forget, on Thursday, there will be a quiz at the start of class on series circuits. Okay, so I will give you a series circuit similar to what we did here, not exactly the same, but I might ask you to solve for REQ and the IT and find some resistor voltages, find some using voltage division. Remember, if I just left it open-ended like I see up here, solve for VR3, if you wanted to do that with voltage division, that would be fine. Would make sense to do it considering you just found IT, but if you hadn't found IT, you could have done it any way you want. But if I specify a specific method, you've got to show me that method, because what I'm really saying is show me you understand that method. So on Thursday, there'll be an exam on series circuit, not an exam, a quiz on series circuits. Okay, so let's talk about parallel circuits. All right, so let's look at this for a minute. If we think about a parallel circuit, as he just starts to draw a series circuit. And I'm going to draw a 3 resistor circuit. You can use, this will apply to as many resistors as you want. If I think about the total current, IT, the current leaves the battery, V sub S, and starts to travel. It wants to get back to the negative terminal, and it's going to go any way it can. So what's going to happen is when it gets to R1, the current's going to split. Part of it's going to go this way, and part of it's going to go this way. We can call this part I sub R1. What's ever left when it gets to here splits. Part goes this way and part will go this way. We can call this part I sub R2 and this part I sub R3. If I really wanted to know what the current was here, the current right there would be I sub R2 plus I sub R3, right? Because this splits to become I sub R3 and I sub R2. All right? So then my question gets to be, if I wanted to know, what would IT be equal to? Ideas?
Would it be equal to I sub R1 plus I sub R2 plus I sub R3?
It absolutely would. So this would be I sub R1 plus I sub R2 plus I sub R3. As a matter of fact, we call that Kirchhoff's current law. So Kirchhoff developed a law for series circuits, which was Kirchhoff's voltage law, and also developed a law for parallel circuits called Kirchhoff's current law. And just as there were 2 ways of specifying the current, specifying Kirchhoff's voltage law, there were 2 ways. There's 2 ways of specifying Kirchhoff's current law. If you remember, the voltage law said the supply voltage was equal to the sum of the resistor voltages. That was one method. The parallel equivalent to that would be the total current is equal to the sum of the individual resistor currents. And if you remember, then in the series circuit, the voltage law said that if I add up all the voltages around a closed loop, then that voltage, total voltage, was equal to 0. In Kirchhoff's current law, it says that the sum of the currents at a given node is equal to 0. And generally, as a rule, we usually use the guideline that currents entering, going into the node, are positive, and currents leaving the node, going away from the node, are negative. Okay? So let's do a sample problem to verify those two and illustrate those two. So let's say, for example, we had this circuit. Let's say R1 was 1K, R2 was 2K, R3 was 200 ohms. And let's say that VS was 20 volts. We could say V sub R1 is going to be I sub R1 is going to be V sub R1 over R1. So I have 20 volts divided by 1K, 20 milliamps. I sub R2, V sub R2 over R2, 20 volts divided by 2K, 10 milliamps. I sub R3 is V sub R3 over R3, 20 volts divided by 200 ohms, 100 milliamps. Okay, so if I use, this is the first form, this is the second form. We could say IT, IR1 plus IR2 plus IR3. So I've got IT is equal to 20 milliamps plus 10 milliamps plus 100 milliamps. So if I add all of that up, that says that IT is equal to 130 milliamps. The second form, and I want to do a problem with that. So what we're saying is that this current is 20 milliamps. This current is 10 milliamps. And this current is 100 milliamps. Now remember last time we drew the node and we said the node is, we go alongside the wire till we get to a turn, we turn. We get to the component, we jump over the other side and turn back. We got to turn because we don't want to cross a wire except at a component. We get to here, we go down, get to the component, jump over, go back in the opposite direction. We turn, go down, hit a component, go back. I'm going to draw it this way because it's easier for me to draw in a straight line. So all of this is my node. And we said that the IT going this way, leaving the battery, is 130 milliamps. So if I was using two, oops, I could say that the sum of the currents is equal to 0. And remember we said currents entering are positive, currents leaving are negative. So what we would say is that IT plus, because the IT is going into the node, right? It's going in. I1 is going away from the node. So it's going to be a minus I sub R1. R2, the current is going into R2 away from the node. So that would make it a minus IR2. For R3, the current is going into R3 and away from the node. That makes it a minus I sub R3. And if I add all of that, that has to equal to 0. So if my double check, I have 130 milliamps minus 20 milliamps minus 10 milliamps minus 100 milliamps. And all of that equals to 0. And indeed, it does check, because these three add up to 130, and we said we had 130 going in. Does everybody get the idea of and see why I made the IT to be a positive value and all of the other resistor currents to be a negative value? Any questions on that? Now, where we'd probably use this is if I had something like this. Let's say, I had this. Let's say we were given that circuit and we had an IT equal to 1 ampere. And you sit there and go, oh yeah, but before you did this current, this current, this current, and figured out IT. Now I'm saying I'm going to give you IT, and you've got these three resistors. And actually what we want to find is, what's the value of R3? What we could do is, first thing is we could find I sub R1, which is the voltage across R1 divided by R1. So the voltage across R1 is the 30 volts divided by R1, which is 150 ohms. So what is that, 200 milliamps? Somebody with a calculator want to double check that? 0.2 volts, 2.2 2 amps.
Yes.
And I sub R2 is V sub R2 over R2. So I have 30 volts divided by 100 ohms, which is 300 milliamps. Again, IT, so let's draw the node first. Here's my node. Whoops. Should have made this a little bit bigger. The IT is over there. R1 current is down here. R2, R3. So again, the total currents going into the node, the current for R1 is leaving the node, current for R2 is leaving the node, current for R3 is leaving the node. So if I say the sum of the currents equals 0, that means that I have IT minus IR1 minus IR2 minus IR3 equals 0. So I have 1 amp minus 200 milliamps minus 300 milliamps minus I3 equals 0. If you bring the I3 over to the other side, you get 500 milliamps is equal to I3. So there's my current for I3, current I3, which is for resistor 3. So now I can use Ohm's law and say that R3 is V sub R3 divided by R3. So we have 30 volts divided by 500 milliamps. No, that's, yeah, 60 ohms. So just as with Kirchhoff's voltage law, we can use it as a check if we're given everything, but we can also use it to find unknown values, which in this case was IR3. I could also have used the other form of Ohm's law if I said IT is equal to IR1 plus IR2 plus IR3. If you think about it, if I took IR1 and added it to both sides, I'd end up with a plus IR1 to the right of the equal sign. If I added IR2 to both sides, I'd end up with a plus IR2 on the other side. If I added I sub R3 to both sides, I'd end up with I sub R3. Didn't know both of them. I'd end up with this form. So if I look at this form, or I look at this form is nothing more than if I took these and just moved them to the other side. So we'd have over here, 1 amp is 200 milliamps plus 300 milliamps plus I sub R3. giving me an I sub R3 of 500 milliamps. So both of these approaches, whether I use this approach or this approach, we end up with the same 500 milliamps for I sub R3. So whichever you're more comfortable with is what it boils down to. Questions up to here? Yes, no?
Not really.
Can you go back to the last slide?
Sure.
Yeah. Right, thank you.
Okay. Yeah, if I move ahead to another sheet and you're not done with that, somebody's got to just say, can you move back? Thank you for doing that. This is the one bad thing about virtual learning and whiteboard. On a regular blackboard or whiteboard in a classroom, you move from one board to the next and whatever you spoke about before is still up on the screen or up on the board until you go back and erase it. Whiteboard, once I move to a different screen, what was there is gone until I bring it back. So don't hesitate to ask.
So the reason why you put a negative sign in front of them is because they are leaving, you say?
Yes, the convention is, we said up here, the convention is that if the current is entering the node, it's positive, and if the current is leaving the node, it's negative. If I flipped positive and negative, you'd still get the same result.
Oh,
In other words, if I made current entering to be negative and current leaving to be positive, you'd still end up with the same result. But the convention is generally accepted that currents that enter we call positive, currents that leave we call negative.
All right, thank you.
Okay. Anybody else need more time on this one before I go to the next one? Anybody need more time on this one before I leave it?
Yes, just 1 second, please.
Okay. You're not writing notes while you're driving, I hope.
Taking screenshot.
The video will go up this afternoon if you just want to wait until then and drive
Oh,
safely.
thank you. Thank you so much. Okay.
Okay. So let's look at this. We just figured out that IT was equal to IR1 plus IR2 plus IR3. And we could say, but wait a minute, IT is VS over REQ. Isn't that how we defined IT? And IR1, since this is a parallel circuit, is VS over R1. And IR2 is VS over R2. And I sub R3 is VS over R3. If I take this thing and multiply both sides by 1 over VS, I get 1 over REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3. If I take the reciprocal of both sides, so think about it this way. Put that in brackets. If I take the reciprocal of the left-hand side, I get REQ. If I take the reciprocal of the right-hand side, all of this goes into the denominator. So I'm left with 1 over R1 plus 1 over R2 plus 1 over R3. And that's how we calculate the REQ for a parallel circuit. And that's also why I call it REQ and not RT. In reality, it is a total, but it's a total of the reciprocals. But my past experience has been, if I call this RT, whether it's a series or a parallel circuit, students just want to add resistor values, and that gets them the wrong answer when it's parallel. So I really like to call it REQ, and you remember in a parallel circuit, you take 1 over the sum of the reciprocals. So for example, let's calculate REQ for this circuit. And by the way, I'm going to put a dot here, which means if you got more resistors, you just keep adding reciprocals. So let's say we had R1 was 1.5K, R2 was 600, R3 was 1K, R4 was 300. If I wanted to calculate REQ is going to be take all the reciprocals and then take the reciprocal of that. So if I do that, it should come out to be 150 ohms. Let's talk about the calculator a minute. On the calculator, what I would be putting in is left paren 1.5 EE second EE. Oh, not milli. 3 x to the minus 1. Plus is it 600? So what you did here was you took the reciprocal of the first one, added the reciprocal of the second, added the reciprocal of the third, added the reciprocal of the fourth. You hit enter. So that's the total of the reciprocals, what we have in brackets down here. And then you hit reciprocal again. That's to get this. And then hit enter to get your result. So try that on the calculator. Make sure you come up with 150. The other alternative would be to put 1 divided by 1.5 EE3 plus 1 divided by 600 plus 1 divided by 1000 plus 1 divided by 300, enter, and then do the reciprocal x to the minus 1. The reciprocal key is easier. Everybody come up with 150? Anybody still there? Nobody's there?
Yeah.
Yes.
Oh, okay.
Yes.
Had me worried for a minute. Thought maybe I was just talking to the ozone. Okay, let's have you try one. Anybody need more time on this before I leave it? Take a minute and try that one.
Oh, Professor, I was just remembering. I know that you said that we had like a quiz on Thursdays, but are we gonna get our test results anytime soon?
Yeah, I want to try and give that to Atwood, and he can give them back to you on Thursday. Would you
Okay.
see the whole? You see him for lab in this class on Thursday, right?
Yeah.
Oh, but are you doing virtual labs now?
Yeah, we're
Yeah.
doing virtual labs.
Oh man.
No, but he said Thursday is gonna be face to face.
When did he say that?
Yesterday.
Oh, okay. Oh, in your 103 class or whatever.
Yeah.
Okay, because like some of us have classes with him for everything, but some of us don't. Like I know some kids are in like the 110 class with him, but they
Yeah.
don't have
110, 103, and 112.
yeah, like some kids don't have everything. But I
Uh,
gotcha. Okay, so I guess Thursday.
all right. So what I'm going to do is I'll probably drop off the exams either tonight or tomorrow, and that way he can give them back to you, and then we'll go over them on Tuesday.
Okay.
Because
Thank you.
I graded him like the weekend that I guess you took it on Thursday. I had it graded by Saturday. But I have one person that hasn't taken it, but I'm going to have to work my way around that and figure out something else. But for now, yeah, I'll drop him off tomorrow or tonight, probably tomorrow.
I have a question.
Yeah.
Didn't one of the students in our class get COVID? So weren't we not scheduled to come back yet, or are we?
I don't know.
back?
The lecture part's strictly virtual.
No, he said that that he was cleared to go back tomorrow, so that's why Thursday we got face to face.
I'll touch base with him and maybe, actually, you know what?
What do you mean? When did they clear him? Because that
All right.
happened
Hold on,
how
hold on,
long
hold
ago?
on.
Like
Wait, time out. Let me do this. Let me shoot him a text right now while you're working on this problem, and I'll see if he can drop in at the end of our class and square away, and then we'll work out who's doing what. But in the meantime, work on this one.
I have a technology question. When you use that whiteboard,
Yeah.
can you make a dot?
Can I make it what?
Like 1.5, can you write the point? Do you have to actually draw it as a circle, or it will let you just do a point?
Oh, you mean like if I needed a dot to just,
Yeah.
wait a minute, hold on. If I just do that?
Yeah, it won't let me do that. It makes like as if there is it's sensing something, or
I
I
don't know
have
that.
to actually make a large circle as a dot, but it won't let me just draw.
You're in whiteboard, WHYTE board?
I don't know. Let me check. I downloaded something from the internet that was free. Is that version free?
Yeah, whiteboard is free.
Okay, hold on just a second.
It's WHYTE BOARD. And I
Yeah,
think you can download it from SoundForge, if I remember right.
Yeah, I'm using version. It's YHYTE board version 0.41.1.
I don't know which version I've got right now, but
It should be.
I've got version.
Yeah, I'm using that one.
Yeah. 0.41. I had, it's funny, I had issues the other day with it. If I tried to use when I was going to do actually for this class, do a homework solution or a class problem solution, I don't remember. And I went to use one of the screen capture programs that I've used in the past. And it started giving me these, when I went to write, it would start giving me this line from the upper left-hand corner of the screen, like way up, like it looks like
Yeah,
it was coming
I
from,
know. I also had that glitch, but this is kind of a glitch. But the point, I never overcame the problem with the dot.
I don't know, I'm using a Tercom pad, and you know, no stylus intent pad on it. I don't know.
I'm using. Let me show you.
It could be an issue with that.
I'm using this,
Okay, I don't know what.
and
It might just be an issue with the software on that end, on the end
Yeah.
with the. But overall, I've been happy with the whiteboard program, other than when I try and use it with a screen capture. And I never had that problem before I went to the newer version of the screen capture program. But okay, by now everybody should be done. So let's take a quick look. I shot Professor Atwood a text. I haven't gotten a reply back. So, oh, excuse me. So REQ is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 we take the reciprocal of the whole thing. So that means I got 1 over 10K plus 1 over 680 plus 1 over 1K plus 1 over 2K, and a reciprocal of that whole thing. So you should have come up with 325.7 ohms. One rule about REQ. REQ must be less than the smallest resistor. So if I look at these 4 resistors, I know my REQ had to calculate to be less than 680. So that's a rule you can always use as a quick double check. The second thing, if you want it, and this is not as critical, but the range, REQ, we said has to be less than R smallest and it has to be greater than or equal to R smallest over N, where N is the number of resistors. So right now, that would mean for this example, REQ has to be less than 680. And for this, if we want to take it to this one, REQ has to be less than or equal to 680 over 4, because we had 4 resistors. So it's greater than or equal to 680 over 4, less than 680. 680 over 4 is what? 145? That right? $170. Higher level math gets me again. And our answer of 325 certainly falls between 170 and 680. Okay. Anybody need more time on this before I put up a new sheet? While we hang around and see.
Yeah, I need a little more time, please.
Okay.
All right, thank you, Professor.
Okay. Anybody else need more time? So let me put up another one. So try that one. Calculate the range for REQ and then check, calculate the REQ value and see if it falls into the range that you just calculated.
R3 is 470 or 490 or something.
470.
Okay, thank you.
Ah, all right, we got about 4 minutes left. Professor Atwood just checked in the room. Let's go through this very quickly, and then we can talk to him about what's going on Thursday. So the range, REQ, has to be less than or equal to R, let's call it R smallest, over N, and less than R small. So our smallest resistor of the three is 220. So 220 over 4. All right, so 220 over 4 is 55. So REQ, when we do the calculation, has to be somewhere between 55 and 220. That's the range we are looking
It's
for.
3 resistors actually, so it's 220 divided by 3.
Oh, thank you.
Yeah.
My
And you
head's
put 222 too.
so what is that? 70,
73.33.
73.3. All
Yeah.
right, so it's got to be greater than 73.3, less than 220. So now if we calculate REQ, it's 1 over R1 plus 1 over R2 plus 1 over R3. We take the reciprocal of all of that. So I've got,
So the range is just a way to find to verify REQ.
yes, just so that we know. So in other words, if I calculated a number here of 14, I'd know that it was wrong. Or if I calculated a number of, and here's where the problem we had over on the other side over here is probably where you'd see more of a problem than you do over here, because guaranteed somebody is going to come up with, in here, if I gave this problem, somebody's going to come up with an answer of like 0.4 ohms, because they enter 10 reciprocal, 680 reciprocal, 1 reciprocal, 2 reciprocal, and forget all about the Ks. So by doing the range first, if you do that mistake, you at least come up and go, wait a minute, my answer is not even close to what I figured out doing the range. So if I came up in this problem and said, my REQ is 0.642 ohms, and I go, wait a minute, it's supposed to be, can't be less than 170. How did they get 0.6124 or wherever it was? All right, so yeah, it's a way of confirming that you've got, you haven't made some really bonehead mistake.
Thank you.
Professor, Professor Atwood didn't, this is a little off topic. I was gonna say this, Professor Atwood didn't contact you back just yet, right?
No, I just said he just checked into the room, so I want to finish this up quick so we can talk to him.
Oh, okay.
So I come up with 128.7 ohms. And that does indeed fall into my expected range of between 73 and 220. So I would buy that as an answer that I'll write down. Okay, any questions on either finding the range or calculating REQ? Okay, Professor Atwood, we had a question. My game plan was that I was going to drop off the exams at the college, and you could give them back when you meet on Thursday. But we weren't sure because there's conflicting stories of whether or not Thursday is a virtual class meeting for lab or a face-to-face meeting for lab. So I figured I would text you and you could explain what's going on.
So right now, ELT110, which is tonight's lab, is virtual. So it's not going to be at the college, right? But as of now, the ELT112 lab on Thursday is face-to-face. We are on for Thursday. So I will meet you guys in the flesh at Nassau Community College on Thursday.
Okay, so if I dropped off the exams tomorrow and put them in your mailbox, you could just send them back?
That would be fantastic.
And then I'll go over them on Tuesday? You don't have to go over them.
We could go over them in class if you want.
Okay, if you want to do that.
Sure. And then if they have any other questions or whatever, they can see.
Yeah, I
you
know
on.
there's one question that the way I marked it, I know I'm going to get some questions on it, and what I wanted, I'll talk to you about that later, but
Sure.
I'll give you a call. But
Okay.
I know where I graded a certain way to see whether or not people who solved the problem solved it because they knew what they were doing or just took a random guess kind of thing.
Right.
Okay.
Absolutely. Okay, good.
All right, so y'all heard that? You know, you're going on Thursday to lab, and I will drop off the exams. Professor Atwood will give them back.